Hi, welcome back to Unit 12, magnetic field. Sorry, I always forget the title of this unit. Magnetic fields and electromagnetism. This is topic 12.3. This is the Biot-Savart Law. And so what this law does is it really helps us calculate or derive expressions for magnetic fields that are caused by electric currents. And so that's what the Biot-Savart Law does. It defines the magnitude and direction of a magnetic field created by a current. It's given by the equation d sub b, or dB, is equal to mu 0 over 4 pi. Okay. I, the current, dl cross r hat divided by r squared. Okay. Now I know there's a lot going on in this equation. Mu 0 is that magnetic permeability, 4 pi constant. I is the current that is going through the wire. Okay. dl is the length of the wire. Now this r hat notation is kind of a strange one. So the thing to remember, r hat is a unit vector along the radius, right? That it has a magnitude of 1. Okay, but it's perpendicular, right, to L. So what does that mean? Well, remember, to replace the cross, right, dl cross r hat, we would write dl r sine theta. So if this is 1 and theta is 90, well, the sine of 90 is 1. So the only thing left over really is dl. Okay, so that cross r hat notation does not affect, right, anything really. You can almost, if you want to write the magnitude of dB, right, or of B, you can just simply get rid of that dl, right, and you would divide it by r squared. Okay. Now, the magnetic field vectors around a small segment of a current carrying wire are tangent to concentric circles centered at that wire. And so you'll see it here in a picture here in a second. Biot-Savart law can be used to derive the magnitudes and directions of magnetic fields around segments of current carrying wires. So if we have the magnetic field of a loop of wire, be mu 0 I over 2r. And when we get into the example, you'll see that we'll kind of revisit that here in a minute. And then finally, a magnetic field will exert, not exerted. So we'll exert a force on a current carrying wire. So FB will be the integral of I dl cross B, right? Or simply ILB sine theta. Okay. But again, right-hand rule will help you figure out the direction of that. Okay, so let's look at an example. So here we have a wire carrying a current of I in a circular arc with the radius r swept through an arbitrary angle theta. So we want to not necessarily calculate, but derive the magnetic field at the center of this arc at point P. Okay, so we want to figure out, what is the magnetic field at that point in the center. Okay, so we always start with Biot-Savart. So dB equals mu 0 over 4 pi. I dl cross r, should be r hat, not r, divided by r squared, right? And so for me to get b by itself, we'll take the integral. In fact, we'll change the integral spot because mu 0 over 4 pi is a constant. So we can actually put the integral here, so we don't have to worry about pulling it out later. One thing that you can also pull out is the current. That will be constant, so I can take that and put it out front here. But again, Remember, this cross R hat is just simply going to be 1, okay? And so we rewrite this as B equals I mu 0 over 4 pi, the integral of RDL, oh, sorry, not RDL, it's just going to be DL, right, over R squared. Okay, now, what is DL? Well, that's going to be the length of the wire, right? Which, if we just have an arbitrary, right, it's the arc length, so it's going to be S theta. But theta is what's going to be varied, or it should be not S, but R. Because S equals R theta, right? So that's going to be R. But theta is what's going to be varied, so DL is going to be R d theta. So I'm going to take that and substitute it in there. So I get the integral. Oh, I always forget that first part. I just want to do integrals, right? Get it done. So it's going to be mu 0 I over 4 pi, the integral from 0 to theta of R d theta over R squared. Okay, so do a little cleaning of this up. That goes away, right? But R is constant, so I can actually pull it out front because our variable of integration is theta, not R. So now I have mu 0 I over 4 pi R, the integral of d theta from 0 to theta. Well, theta, right, that's like, there's a 1 in front, so the integral of a constant is just simply our variable of integration. So mu 0 I over 4 pi R theta times theta evaluated from 0 to theta. Well, that's easy. That just makes it theta. So mu 0 I theta over 4 pi R. So there is, right, the magnetic field at point P. Now, as I said, let's revisit that loop, right? So let's go back here. So we have B equals mu 0 I theta over 4 pi R, not 2 pi R. Jumping the gun a little bit. So for a loop, theta is 2 pi. So let's plug that in right there. So B equals mu 0 I times 2 pi divided by 4 pi R. And now clean this up, right? Cancel things out that can be canceled out. Pi, that 2 cancels a 2 on the bottom. And so look what happens. So the loop is going to be mu 0 I over 2R. And look what we wrote right there, mu 0 I over 2R. Okay? So this is the Biot-Savart Law, right? So this will help you calculate or derive expressions for the magnetic field, with current carrying wires. Okay, and then we also talked about the force of current carrying wires. Okay, and so in the last topic for this law, or for this unit, we're going to look at Ampere's law, which is kind of, we've already talked. We were mentioning that a little bit earlier. Okay, with that B dot dA, or in this case, it'll be B dot dL. Okay, so we'll get into that here shortly.